Hi everyone, welcome back. In this section we are going to look at changing variables for double and triple integrals. So let's have a quick reminder, take our time machine back to Calculus 2 and have a quick reminder about changing variables there. So in this example we want to evaluate this integral. And your first reaction might be, let's do a substitution. It looks like if I substitute for whatever's under the square root sign, the derivative is out front, and so it should simplify the integrand, and in fact it does. So for our substitution we change our variables, and then we also have to change our differential, our dx, and they get updated in this way. And so our new integral becomes, well, the x dx becomes a 1/2 du, and then the square root of 1 plus x squared, that becomes a root u. But we also have to update the limits of integration. So what do our limits become? Well, we have x ranges from 0 to 1, and so our new limits in the u variable, u goes from 1 to 2. And so there's our updated integral. Now what we have done here is effectively we have taken an integral involving variable x and changed its variable to an integral involving the variable u. So we've done a change of variables. And this is precisely what we want to do in this section, but for double and triple integrals. We want to change into different coordinate systems or different variables. In terms of a picture, what we have is that our original integral was over the x-axis from 0 to 1, but then we converted that to an integral over the u-axis from 1 to 2. Now, we never drew these pictures in Calculus 2 because, well, they're not very interesting. It's just we went from one interval to another interval. But for double and triple integrals, we're going to go from one region to a different region, and so we're going to want to sketch how these regions have changed. And so this kind of picture we will do for double and triple integrals. Now, one last thing I want to address about substitution in general is that we've taken an integral, like the integral of f of u du, and we've related it to an integral of f of g of x, g prime of x dx for u equal to g of x. So this is what we've done. We've related these two integrals. We started with essentially the one on the right. That was our example. We made a change of variables, u equal to 1 plus x squared, and we converted it to the integral on the left. But I've written it in this way with the integral we eventually ended up with on the left because in what we're about to do, it makes a little bit more sense to think about it this way. And here's the reason why. I've got this integral, f of u du. What I'm going to do is I'm going to replace u with some expression involving x. So we do that. We take our u, we replace it with an expression involving x. That gives us f g of x. But then I also have to take the du and replace it with an expression involving x. And that becomes this updated length element. And we can see that the way the length element got updated was it was related to a derivative of the change of variables. And this is what we want to explore. How does the area element update? How does the volume element update when we make a change of variables? And it turns out it's related to the derivatives, but in this case they are partial derivatives. So there's partial derivatives that get involved in making up that change in the area element and the volume element. We've already seen the result of some of these changes. For example, in polar coordinates, the update was r dr d theta. So r came about from some way. We looked at it in terms of geometry, but we'll see that it actually comes out as related to derivatives of the change of coordinates from x and y to r's and thetas. And similarly for spherical coordinates. If we're thinking about how that volume element changed, there was a rho squared sine phi. We're going to see how that came from considering partial derivatives. So that's our goal, is to investigate how to do this substitution in general for double and triple integrals. Let's just remind ourselves with how things get updated in triple integrals. So we've got this region closed by a sphere of radius 3, just in the first octant. And this is a spherical box, because the inequalities that describe it are rho goes from 0 to 3, theta goes from 0 to pi by 2, and phi goes from 0 to pi by 2. So in spherical coordinates, this is a very nicely described region. What do we do in order to compute the triple integral? Well, the first thing we have to do is figure out how do our limits of integration get affected, and those are coming from the inequalities above. So we've got theta goes from 0 to pi by 2, phi goes from 0 to pi by 2, r goes from 0 to 3, and we've also got our integrand. Our integrand in this case is the square root of x squared plus y squared plus z squared, or e to that, and so that becomes e to the rho. And then we've got our volume element update, and that becomes our rho squared sine phi, and then we'll get our order d rho, d phi, d theta. And this little aspect here comes from the volume element. And what we're going to show is that in general we can argue that this comes from some combination of the partial derivatives of the change of coordinates. And that's what we're hoping to get to. General change of coordinates, how do we get this change in the volume, or the volume element? It's going to come from these partial derivatives. So we'll see that. We got it from geometry in the last section, but we'll see how we can get it a different way in this section using partial derivatives and a little bit of linear algebra. Okay, so let's get our feet a little bit wet with an example of a different coordinate system. So this first part is just exploring the integral, getting a feel for what it's going to take to integrate it. Let's see what it takes. We want to integrate this e to the x plus y over x minus y over this trapezoidal region. So we've got the point 1, 0, 2, 0, 0, negative 1, and way down here is 0, negative 2. And we're looking at the trapezoid that has these 4 vertices. So we can connect them up by straight lines. So this is the region we are interested in. Now the problem is, if I want to integrate over this region, let's say I want to integrate over the y direction first. Then I'm going to have to integrate. I can see here that the bottom curve is the straight line or diagonal line, the top curve is that diagonal line, but then at some point my top curve switches. So I'm going to have to use 2 integrals in order to do a y first integral. But that same argument holds for an x first integral. There's a definite left diagonal curve and a right diagonal curve, but then at some point I switch. My left curve becomes a different curve. So I'm going to have to use 2 integrals there. So that's one aspect. I need 2 integrals depending on whether I want to do y first or x first. The other thing is the integrand itself looks to be difficult to deal with. Our integrand is e to the x plus y over x minus y. That looks challenging to integrate. So we've got two issues that we're really faced with here. Integrand looks difficult to find the antiderivative of, and the second one is region requires two integrals. So there's a couple of issues to deal with. Maybe if we change coordinates, that these problems will go away and we can make the problem simpler. And so let's put a pin in this example just temporarily and have a look at this next problem. We're given a transformation, so how to go from UV coordinates to XY coordinates. And this is a linear transformation. It's a linear transformation because the functions that describe x and y are linear functions in u and v. So it's a linear transformation. It's something that we would have seen in linear algebra. What we want to do is we want to find the image of this region in the UV plane. Find what that image is in the XY plane. So what is this region in the UV plane? Well, V is trapped between 1 and 2. So maybe we'll say V is equal to 2, V is equal to 1. And U is trapped between negative V and V. So there's these two lines. There's U equals V and U equals negative V. And we're interested in the region where V is below 2, above 1, and U is to the left of U equals V line and to the right of U equals minus V line. So this is our region we are interested in. And what I want to do is I want to find out what happens to this region when I map it over into x, y coordinates. So the way I'm going to do that is I'm just going to focus on these 4 points. So basically I want to know every one of these points in the blue region, where does it go? And what region does it fill out in the x, y coordinates? So I'll start with a couple of points just to get a feel. So we'll start with point A, 1, 1. Well, if I plug 1, 1 into our formulas up above, so u equals 1, v equals 1, then I get x equals 1 and y equals 0. So there's our point A prime, the image of A, becomes 1, 0. What about B? That's 2, 2, and that goes to 2, 0. So that's B prime. What about C? That's negative 2, 2. So if I plug in negative 2, 2, I get x is 0, and y is negative 4 over 2, or negative 2. That's down here. And that's C prime. And lastly, D prime, which is negative 1, 1. So that's D. D prime goes to 0, negative 1. So there's the image of our 4 points. Now what we can do is we could say, well, I figure out where points went to. Maybe I could start writing down the boundary curves, parameterize them, each of the boundary lines, figure out what their image is. But here I note that it's a linear transformation. And so linear transformations mean that lines go to lines. And so the line that connects A to B must map to a line that connects A prime and B prime. So this line must go to this line. And the one that connects B to C must go from B prime to C prime. And similarly, 1, 2, 3, and the last line from D back to A goes like that. So linear transformations take lines to lines. So because I know where the vertices went and now I know where the boundary lines go, I actually know where the whole region gets mapped to. And so there's the image of that region under that linear transformation. And then what we notice above is that that's precisely the region we were trying to integrate over in that previous integral. So if I use this transformation to convert between u's and v's as an x and y's, integrating over this region involving x's and y's would be equivalent to integrating over the region involving u's and v's on the left. And that region is easier to integrate over because u would go from negative v to v and v would go from 1 to 2. Much simpler region to integrate over, only one integral required. But the subtle aspect is, sure, I can take my original integral now at the top of the page. I could rewrite my integrand by just taking whatever x is in terms of u and v and y in terms of u and v, just plug them in there, simplify my integrand. I get my region of integration. It's now just this region on the bottom left. The problem is the volume, or the area element in this case, dA. How is dA going to change? How are the areas of a small region in the UV coordinates, how is that related to the area of the corresponding region in XY coordinates? That's what we need to investigate. So that's the final piece of the puzzle in trying to change coordinate systems, is how does the area element change? So how does the change of variables affect a double integral? In particular, about the area element. So let's look at our transformation. We had x and y. That was equal to t of uv. And this is 1/2 of u plus v and 1/2 of u minus v. But we could write this as a matrix multiplication. It is 1/2, 1/2, 1/2, negative 1/2, and then uv. So there is our matrix transformation. And so this is a linear transformation. We already knew it was linear. This is it written as a matrix. And for this matrix, we could do some things. We can compute its determinant. And what do we get? So the determinant of the matrix is, we can write it with these vertical bars around it, 1/2, 1/2, 1/2, negative 1/2. And that's going to be negative 1/4 minus 1/4, or in other words, negative 1/2. And the question is, what does that number mean? What does this number mean? What does negative 1/2 mean? Well, the negative part tells us something. We'll get to that in just a second. But the 1/2 is our area scaling factor. So this 1/2 tells us that if I had a region in UV coordinates and I looked at what its image is in the XY coordinates, the area of the region in the XY coordinates, its image, would be half the area that it was to begin with. And let's see why this is the case. So what we'll do is we'll just look at a particular region. I'll look at a region of area 1. So we got a 1, this is in UV coordinates, and I want to know, what happens to this area. What does this area become when I map it into XY coordinates? So how are we going to figure this out? Well, one of the ways to do this is to just say, I know this vector. That vector is vector 1, 0. And this vector is vector 0, 1. These we've called in linear algebra, for example, the standard basis vector, so that would be the E2 vector, or if we want, we could just call it j hat, like we've been doing in this course. This other vector would be called E sub 1, or I can just call it I hat. And then what I can do is I can say, what is the image under this mapping T of I hat? Well, it goes to the vector. I can just look at my mapping up above. If u is 1 and v is 0, then it goes to 1/2, 1/2. So it goes to here. So that's T of I hat. That goes to 1/2, 1/2. Maybe I'll just write it up here. 1/2, 1/2. And similarly, I can see what is T of j hat. That goes to 1/2 minus 1/2. And so that whole region, because it's a linear transformation, that whole region gets mapped to this region here. And so what is the area of this region? Well, because that each of those side vectors are, well, let's look at ti hat. It's 1/2, 1/2, so I know that the length of this side is 1/2 squared plus 1/2 squared square rooted. So it's 1/4 plus 1/4, that's 1/2 square rooted, so that's 1 over root 2. That's that side length. This side length is also 1 over root 2. So the area is 1 over root 2 times 1 over root 2, or 1/2. So we started with an area of 1, and its image was an area of 1/2. And that's precisely what this determinant is telling us. It's telling us that if I take the absolute value of the determinant of that matrix, 1/2, 1/2, 1/2, negative 1/2, if I look at the absolute value of that, that's 1/2, and that's the number I'm interested in, because that tells me my scaling factor. Now what else do we get? Well, it turns out the negative sign also tells us something. Notice in our first diagram, the one on in the UV plane, if I take I cross j and think about what the vector points in the direction of, in other words, I'm just trying to figure out how are I and j related to each other in terms of positions. Well, if I put my fingers in the direction of I, curl them in the direction of j, my thumb points out of the page. But if I look at their images, put my fingers in the direction of ti, curl them in the direction of tj, my finger points into the page. So somehow there was an orientation that switched here. In some sense, there was a flipping effect that happened. And that's what the negative 1 is telling us, or the negative sign is telling us in the determinant, that there was a flipping effect. So there was a scale change, that was the 1/2, and there's a flipping effect. I don't care about the flip. I don't care about the orientation change in terms of area. I just care about the scaling factors, and that's where that 1/2 is coming from. You can also see that effect of the negative 1 in terms of the scaling change in our previous diagram, or sorry, in the flipping or the orientation change. Our previous diagram, if I look at the UV plane on the right, we've got our trapezoid being traced around the boundary in a counterclockwise direction, but then when I look at the other diagram, it's going in the clockwise direction. And so there was a change of effect there that we see, and that's really that's telling, the negative sign in the determinant really tells us that this has to happen. So that's what the negative is telling us. There's an orientation change, the magnitude of the determinant telling us there's a scaling factor change, and the scaling factor is what I care about. Now if we think about where that scaling factor came from, it came from the determinant of the matrix, but now I want to take a step back and say, okay, what if my functions weren't linear? What if there wasn't a linear transformation? Well, one way to notice where this matrix could come from is by just observing the following. We got it by just noticing it was a 1/2 u plus a 1/2 v and a 1/2 u minus a 1/2 v, but we could notice that this is also equal to the derivative of x with respect to u and the derivative of x with respect to v, because that's just a 1/2 and a 1/2. And this was the derivative of x with, y. For the second row, it's the derivative of y with respect to u and the derivative of y with respect to v. So this is telling us that, hey, maybe in the case where it's not linear, that we can get this scaling factor by looking at the determinant of the matrix of partial derivatives. And so that actually turns out to be the case, and so we give that matrix a name. This matrix is called the Jacobian of the transformation. And so if I have a transformation x is g of uv, y is h of uv, then the Jacobian is just the determinant of the matrix of partials. And that ends up being the key, the missing ingredient that we need in our change of variables. That's the area is now updated, and that's our new area element. And so this is, as we alluded to before, it should be related to the derivatives. In fact, it's related to the determinant of the matrix of partial derivatives. And so the question you might have now is, why? I've only done a linear case. And it's true in the linear case because it was linear, after all. Why is it true in the general case? So let's see. Short answer, though, just spoiler alert, short answer is why it would be true in the general case is because the whole idea of taking derivatives is this process of approximating curvy objects by straight things. So when you take a derivative, you can think more in terms of linear approximation. So I can take my curvy object, I can do a linear approximation of it, and when I do a linear approximation, I use derivatives in that, and those are precisely those derivatives that are coming out. So when I take a curvy object, turn it into a linear object, and then do the linear algebra on the linear object, it's the matrix of partial derivatives that I'm going to be working with. We'll do it in a slightly different way here, so I don't have to lean too much on the linear algebra, but I'll lean more on curves, space curves, stuff that's done in this course. So let's do it that way. So we'll start with the transformation. T of uv is some function x of u and v and some function y of u and v. And we want to know what is the area of a small uv box in the xy coordinate system. So in xy coords. In order to do this, instead of working with this transformation t, I'm going to work with a vector function. So all I'm doing is just turning it into a vector. And so that's what I want to work with. So now the idea is I've got in my UV coordinates, I've got a small rectangular box. And it's going to be trapped between u0 and u1. And v0 and v1. Its width is delta u, also known as du, and its height is delta v, also known as dv. So that's the region we're interested in. And I want to know, when I map that region into the xy coordinates, what is the area of it in the xy coordinate plane. So that region gets mapped to something like, I don't know, maybe it doesn't have to be linear in any way, so it could be curvy. It could be something like this. And so we have our point, let's say, just to get a feel, maybe that point A got mapped to this point A prime. Maybe this point B got mapped to B prime. And this point C gets mapped to C prime. And now I'd like to figure out what is the area of this curvy region. Well, I'm imagining that these boxes are so tiny, because the idea is that these boxes are coming about from chopping up the region into little bits, because that's what we're using in our integral. So these boxes are really tiny. Now, what I'm going to do is I'm going to look at what happens to these sides. So let's look at this side from A to B. Maybe I'll put it in green. Got this side AB. Where does point B go? Well, B goes to B prime. And what is, so maybe I'll back up a little bit. That green line segment's going to this green line segment here. But what I'd like to do is I'd like to approximate it by a straight line. So maybe a vector or something like that. What vector am I going to use? I'm effectively going to use the tangent vector to that green curve at the point A prime. That's essentially what I'm doing here, but I'll get rid of that vector just temporarily. So what's B prime? B prime is R of u0 plus delta u v0. So that's what it is. This is our transformation t, or in other words, our vector function r. So B is given by coordinates u0 plus delta u and v0, so B prime is r of that. And here's where we can use calculus. So I'm not changing v naught at all. So I can think of just this as a function of the variable u. So when I use linear approximation at the point u naught v naught, what I get is that it's the function value at u naught. And I'll suppress the v naught because it's always going to be v naught in this line. We're always using v naught. So it's the function value at u naught plus the derivative at u naught times the change in u. So change in u times the u derivative at u naught v naught. So this is just calculus 1 linear approximation. That's all this line is. And so what this tells us is this is a prime. So what this is this is the approximate, or approximation I should say, approximation to vector a prime b prime. That's an approximation to the vector from a prime to b prime. So it gives us, maybe I'll draw a little vector in here, it gives us a vector that does something like that. And we can do the same thing for c prime. That is r of u naught v naught plus delta v, which is approximately equal to r of u naught v naught plus delta v, r sub v, or the v derivative at u naught v naught. And this is, again, a prime. And what this is a approximation to vector a prime c prime. So that's this vector here. Something like that. It's an approximation to it. So what we've done is we've converted that curvy shaped region we're trying to find the area of to a region that looks like this. A prime vector vector parallelogram. So we've got that region there is approximately this region here. These are approximately equal. The smaller they are, the better approximations they are, and as we go off to infinity, essentially, the number of rectangles going to infinity, these things become equal. So in the integral, these things will end up being equal, but we got a good approximation here. And so now we can say, all right, now let's try to find the area of the region R. We're going to use the area of this region down below, which is a parallelogram. The only thing we need to know are what are these sides. Well, one side vector is, this one up here is delta v, rv, u naught, v naught, and the vector down here is delta u, r sub u, u naught, v naught. And so here's what we have. The area of R. That's the region up above. That's the thing we're trying to find. It's approximately the area of this region. What's the area of that region? The area of that region is the magnitude of the cross product of these two guys. So it's the magnitude of the cross product, delta u, r sub u, cross delta v, r sub v. But I can factor out the delta u, delta v, and I'm just left with the cross product of ru and rv. You might say, but how can you use a cross product? These are two-dimensional vectors. Well, we'll just pad the third component with a 0. So we can write this as, I'll bring the delta u, delta v out to the back. For that cross product, we've got I, j, k, pad it with zeros, and then the r sub u is x sub u, y sub u, and the partial derivative of r with respect to v is x sub v y sub v. And these vertical bars represent the determinant, which is for the cross product. Then we still have the absolute value signs around it. And so this becomes then the absolute value of x u y v minus x v y u delta u delta v, and that's the area of the region R. And this is the Jacobian. That's the determinant of the matrix of partial derivatives. And so that's what we wanted to show. We wanted to show that the area element, the way it updates is, it's the determinant of the matrix of partial derivatives times the du dv. And so there's our Jacobian. So we've just established that this piece is supposed to be right there. One thing to notice about that piece is we do have those vertical bars there. That's absolute value. The Jacobian itself, scrolling up, the Jacobian itself already has vertical bars in it. That means determinant. And then the ones in the integral mean absolute value. And again, why absolute value? Because we're stripping off the sign. We don't care about orientation reversal. We just want to know what is the magnitude of the scaling factor. We don't care about the sign. All right. Let's have a quick example where we find some Jacobians. So we're going to find the Jacobian of these transformations. So it's dxy duv. That's shorthand for the determinant of the matrix dx du dx dv. So notice what we do is we just start with the first one. And the first row is dx du dx dv. And then we go to the next one. And that's our next line, dy du dy dv. So there is method in how we write this out. dy dv, dx du is a half, dy dx dv is a half, dy du is a half, dy dv is negative a half. And so that is the determinant of negative a quarter, minus a quarter, or minus a half. And so there's our Jacobian. How about for the next part? There we're going to do dx dy dr d theta, or dr theta, and that becomes, I'm going to write it shorthand, x sub r, x sub theta, y sub r, y sub theta, which is, actually we'll stop here and we'll just make a prediction. What do we think this Jacobian is? Remember, scroll back, the Jacobian is this thing that's sitting in our change of variables updated integral formula. So it's the thing in front of, in this case, the dr d theta. And so we know from changing to polar coordinates that we need an r there. That's where the r is going to come from. And so we already have a feeling for what this determinant should be. It should be r, or at least have a magnitude of r. And so let's check. X sub r, that's cos theta. X sub theta, that's negative r sine theta. Y sub r, sine theta. The derivative of y with respect to theta is r cos theta. So that determinant is r cos squared theta plus r sine squared theta, which gives us the value of r, which is the one we expected. So now we've got another way to justify the change of variables formula into polar coordinates, and that updated area element being r dr d theta. The r is coming from the Jacobian in this case. Alright, so this first part of the video was all about getting the ingredients we need to do the change of variables. So introducing a change of variables, and then the Jacobian, which is giving us this area scaling factor, and then putting it together. The next part of the video, I've just split up into a bunch of individual examples. So there's 4 additional videos, but each one of them is an isolated example. So you can go ahead and watch them in any order. The first 3 are integrals, double integrals, and the last one extends this idea to triple integrals and spherical coordinates and revisits that rho squared sine phi to see that it actually comes from the Jacobian as well. All right, we'll see you in the next video.